Hello, everybody, and welcome back. This is my fourth try at trying to record this. You gotta love the way technology and the internet works, and I'm fed up. But let's get through this anyways. I thought we'd talk about the local max and min points on a graph. This is really the second application we have to calculus. This is actually a pretty easy one, but it's a very important one that we have. Do notice let me bring up my pen. All right. I'm asking about the local max and min points. And the next lesson, we'll talk about the absolute max and min points. All right. And there's a slight difference between the two. So when we talk about local, all right, these here would be examples of local maximum and minimum point, or local maximum points. All right. And they're local because within that area, if you look to the left and you look to the right, you're going downhill on both. So they're max. This here is a local minimum point because if you look to the sides, right, either to the left or right, you are looking uphill. Absolute is a little different. So actually, I think I'll leave those there. I'll leave. This here is clearly the absolute highest point. I think everybody can see that. That would be the largest y value, whatever that y value is. And the absolute lowest point, well, if these are continuing like it looks like to negative infinity, we'd say negative infinity was the absolute lowest. That's not what we're looking at today. All right. There are applications where you want the locals, and there are applications where you want the absolutes. Today, we are just looking at these points, the locals. So here's the first thing I notice. If I were to draw a tangent line, pretend those are all lines and they're all tangent, at all three of those, what can you tell me about the slope? And hopefully you were all thinking to yourselves, well, I can see that the slope is equal to 0. All right. For a local max or min, we do want to know when the slope is equal to 0. Now, in a calculus class, you would also talk about you want to look for when the slope is undefined, but we're not going to look at any problems where that comes into play yet. All right, that'll be for you next year. What else has to be true? Let me get rid of this. When you have a maximum point, the slopes will go from positive values to negative values. They'll go from uphill to downhill, positive to negative, uphill to downhill. For minimum values, your slope should be going from negative to positive. So what we're going to do is we're going to look at something called a wiggle graph. And a wiggle graph is nothing more than a line, a number line. We will put the derivative, all right, that's a number line for the derivative. We got to find the derivative when the slope is equal to 0, all right? And then we will put any points where the slope is equal to 0 on there. Whatever the first x is, whatever the second x, whatever the third x is. And then we'll look at these intervals here to see what's going on with the slopes. Are you going from plus to minus, which means you have a maximum? Are you going from minus to plus, which means you have a minimum value? Or are you going like from a plus to a plus, which means you don't have a max or a min. It means that you really just had a delay or a stutter in the graph. Okay, so here are the two steps that we take to find local max or min points. In the next lesson, we'll talk about the steps for the absolute max or mins. Number one, you need to find any of the x values where the slope is equal to 0. So in order to do that, you're going to need to know what is the derivative, all right, because that is the slope formula, and then we're going to set it equal to 0 in order to find the max points. Then we're going to use a wiggle graph. This would be the wiggle graph for f prime. And as I indicated, all right, we would put any points. I'm going to write as x1, x2 this time. Any points where the slope is equal to 0. And then we'll check the intervals before and after. So before x1, we'll see what type of slopes we have. In between those two, we'll see what type of slopes. And afterwards, we'll see what type of slopes. And then we can use this information here to determine whether we have a max point, a min point, or whether we have neither one of those delays occurring. Remember, at any point, you can pause this in order to write down anything you need to, but I will continue on. So let's try this example. Find the x values to any local max and min points. Now, I would like you to notice here, I'm asking you to find the x values. Some problems will say, give me the x values. Some problems will say, find the y values. You'd find the x values first and then plug it in the equation to find the y values. Some will say, give me the whole point where you need the x and the y. You just have to pay attention to which one you're being asked for. So in this problem here, I want a local max or min. My two steps, number one, I need to find the derivative and I need to set it equal to 0. So when you're finding the derivative, remember you have the definition of a derivative or you've got the power rule. And you have to ask yourself, is the function set up to use the power rule or do I have to use that longer definition? And in this case, we're all set for the power rule. So the derivative of x cubed is 3x squared. The derivative of minus 3x is minus 3. And the derivative of 2 is equal to 0. So we have our slope formula, and then we're going to set that equal to 0, and you're going to solve. 3x squared is equal to 3. X squared is equal to 1, which means x is both a plus and minus 1. Right? There are two different points here where the slope is equal to 0. Now, that should make sense because if you think about it, doesn't the graph to a cubic equation look something like this, where we should have a max point and we should have a min point? All right, so I'm already thinking that, hey, my maximum point, I think, is at x equals -1 because that number comes first. And then my minimum point would be at x equals +1. Well, here's where we're going to use our wiggle graph to defend this. So I'm going to do a little bit of erasing here because I don't need all of this. I do need to remember that x is equal to 1 and -1. Okay, let me go back to the pen. Let me use black there. Here's my number line. This is the number line for G prime. And on this number line, I need to put any points where the slope was equal to 0. And so what you've done is you've separated your complete number line into 3 pieces. All right, numbers less than -1, numbers in between -1 and +1, and numbers greater than +1. And your job now would be to check one point in each interval and see what that slope is. So how about numbers that were less than -1, like -2? If I go up to my derivative and I plug in -2, I'm going to have 3 times -2 squared. -2 squared is 4, times 3 gives me 12, and 12 minus the 3 is going to give me the 9. Now the 9 is not important to me. The fact that it's a positive 9 is really what's important to me. So what I know is from -∞ to -1, the graph is increasing. We kind of know that's true, don't we? From what the cubic graph should look like, we should be going uphill. How about between -1 and +1? All right, it looks to me like we should be going downhill. So let's try a point in between those like 0. G prime of 0. If I plug a 0 up into my derivative, 3 times 0 squared would be 0, and 0 minus 3 is -3. I do get a negative back, and I was expecting that. Finally, numbers greater than 1, like 2. G prime of 2. If I plug 2 into my function, I'm going to have 2 squared is 4, times 3 gives me 12. Take away 3 gives me, I'm going to get 9 again. I'm going to get a positive slope back. So my graph did go uphill, downhill, uphill, like we expected to. Now let's write the answer. We only needed the x's here. All right, so I'm going to get rid of a bunch of this, and I'm going to bring back my wiggle graph, G prime, -1, +1, and we went from a plus to a minus to a plus. So here's what we have. When x is equal to -1, we have a local max. It's the highest point in that area. Right? We know that from the graph, but we also saw that the slopes went from uphill to downhill. Right? Uphill to downhill would be that max. At x is equal to 1, we see we have a local minimum value because, again, the slope went from negative to positive, negative to positive. All right, now there are problems that might ask you to justify. So if you said x, when x equals -1, you have a local max, you would then state my slopes change signs, right? Or change from uphill to downhill, positive to negative at x equals -1. And I've got a local min at x equals 1 because my slopes change from negative to positive. That's all you have to do. Now, when you get to a calculus class, you're going to be asked to justify. All right, we don't have to worry about justifying, but I do want you to think about it. Okay, second problem, same directions. Find just the x values to any local max or min points. First step, find the derivative. Why don't you go ahead, take 30 seconds, find the derivative to this equation for me. Take that derivative, set it equal to 0, and solve. I got x equals -1. Now, not all the, and not in every problem you're going to get x equals 1, -1, or 0. All right, those are the more common values that we get. It just so happens in these examples we got that. Now we're going to create our wiggle graph. This is the second step. -1 has to go on there. We are testing for slopes. All right, so this is a wiggle graph for y prime. If you plug in a number before -1 into the equation, like -2, y prime of -2 is equal to -2 minus, let's see, I don't like that, minus -2 times -2, which will give me +4, which will gives me a +2. I've got positive slopes here. And if I plug in a number greater than -1, like 0, I'd have -2 minus 2 times 0 gives me 0, and that gives me -2. I get a negative here. So what occurred at x equals -1 if you went from positive slopes to negative slopes? This would be an example of a local maximum point. Why? Because the slope changed from plus to minus at x equals -1. Now, this should make sense. I'm going to erase this. If I had said, hey, I want you to graph that equation for me, I think you would all agree it's an upside down parabola. It should look something like that, and there's definitely a maximum point. The key would be to find that maximum point. Oh, and you've already done this, right? Because the maximum point is the vertex. And don't we have a formula that says x equals -b over 2a? That would help us to find that. Let's see, if I use that formula, the b value is -2. So I want the opposite of -2, which should be 2. Then I have to double a. My a value is -1, so double that, you get -2. And you would have found out your vertex was when x is equal to -1. Well, you now have a couple ways you can do that. If you actually have a parabola, which is very rarely given in calculus, all right, because we already have methods to find a max point there, you can use your formula, all right. If you have cubics and quartics, then you got to use the calculus piece to it. And maybe this is a good point to show this also. Let me erase this. We know how all quadratic formulas are in the form y equals ax squared plus bx plus c. If I had said I want to find all the max and min points on any quadratic equation, y prime, we'd have to take the derivative, equals, see, my derivative here would be 2ax plus my derivative to the second term would be b, and the derivative of a constant is 0. And we are supposed to take that derivative and set it equal to 0 for all local max and mins. And then if you solve this, 2ax plus b equals 0, 2ax equals -b, divide by my 2a, and notice what we end up with is that formula that you have known since 8th grade on how to find the vertex. It actually comes right out of calculus. It is the first derivative to a quadratic, all right, where we take the derivative and we set it equal to 0 because we know that's where high points and low points should be. Okay, let's do one last problem. Let's take this x to the fourth equation. Now, in this case, I'm asking you, what are all the maximum points? So I want both the x and the y. All right, first step, find the derivative. Won't you please do that for me? Take that derivative, set it equal to 0, and solve. If I'm moving too fast for you, just remember, put this in pause. So 20x cubed would be equal to 0 when x is equal to 0, and 1 minus x is equal to 0 when x is equal to 1. Then I'm going to make my wiggle graph, and I'm actually going to get rid of this. I'm going to go back up here, and we found out x was equal to 0 and 1. 0, 1. Here's my y prime, and I do need my derivative to plug into. So the derivative was what? 20x cubed minus 20x to the fourth, or 20x cubed times 1 minus x. And the only reason I'm going to put the factored form back up there is a lot of times it's easier to plug numbers into the factored form than it is to the original expanded out form that I have here. So let's see, numbers before 0, pick anything, -1. I'm going to go down to my factored form here, and I'm going to plug in x equals -1. 20 times -1 cubed is -1, and 1 minus -1 is 2. I can see if I take a positive times a negative times a positive, I'm going to get a negative back. The fact that it's -40, I don't need the 40 part. I just need to know that I have negative slopes there. If you try a number in between 0 and 1, like 1/2, all right, I'm going to go to my factored form again. 20 times 1/2 cubed. 1/2 times 1/2 times 1/2 is 1/8. And then 1 minus 1/2 is 1/2. I've got a positive times a positive times a positive. That gives me a positive. I don't need to know that it's 20 over 16 or 10 over 8 or 5 over 2. All right, I just need to know that it's a positive. And then once you do the same thing for numbers greater than 1, I'm going to pick 2. 20 times 2 cubed is 8. 1 minus 2 is -1. And a positive times a negative is a negative. Okay, our 2 steps. We found out when the slope was equal to 0. All right, we took our derivative, we set it equal to 0. We got our 2 values in this case. We put those 2 values on a wiggle graph, and we can see how the slopes are changing from plus to minus, minus to plus. Okay, now this problem, remember, was a little different. I'm going to get rid of this because I just need the space, but I want to leave some of it because it was asking me for the points. So I'm not just asking for the x value, but I'm actually asking for the x and y. So when x is equal to 0, in order to find the y, you're not going to use the derivative. You're going to use the equation you normally would to find y, right? So I'm not looking for the slope there. I already know the slope is 0, right? I'm looking for what the y value is. So if I go up to my original function and I plug in x equals 0, I can see I get y equals 5 back. So the point 0.05 would be is that a local max or a local min? Remember, you went from negative slopes to positive slopes. So at 0.5, that would be a local minimum value. My second point was when x is equal to 1. And I would plug x equals 1 back into my original equation. 5 minus 4 plus 5 gives me 6 back. And at x equals 1, we went from positive slopes to negative slopes, so this has to be a local maximum point. Okay, that's really all there is to it. Finding local maximums are very easy, well, at least when you have polynomials. When you start getting into trig equations and exponential and rational and all the other types of functions that we've either talked about or haven't talked about this year, right, like you will in a calculus class, it can be a little more strenuous in order to come up with. But we love polynomials, and that's all that we want to start with this year. Okay, here's a couple of problems for you to practice with tonight, and I will talk to you very shortly.